Welcome back. Now we start chapter 35, the reflection and refraction of light. And I've got a lot of good demos about this too, about refraction, reflection. I have a demo also showing how to prove the law of refraction and reflection experimentally. So watch those demos. The law of reflection is pretty simple. When a beam of light comes and hits a surface, we make the normal line to the surface. And we say that the angle of incidence is equal to the angle of reflection. So that's pretty simple. Angle of reflection equals angle of incidence. And then we usually measure with respect to the normal line to that surface, right? Now, if a mirror is a very flat, very plain mirror, it makes a good image because the normal line to the surfaces are all the same. Now, if a surface that is not very flat, it will have little bumps and stuff on it, like this, so that when the beams of light come and hit different portions, the normal lines are all different. So it will come and hit this portion, maybe the normal line is like this, it will reflect like that. Maybe a beam of light will come like this, the normal line is like this, it will reflect like that. You see, so there's microscopic inconsistencies in that surface, and that's why when we look ourselves on a table or something, we don't really see a good image of ourselves because their microscopic inconsistencies don't give a good image. The other reason we don't see a good image is the reflectivity of the surface. Maybe it's absorbing some of the light energy. When we learned in the reflection transmission concept in the chapter 16 about traveling waves, we said when a wave comes, part of the energy is reflected, part of the energy is transmitted. Okay, a good mirror that is meant to reflect will reflect most of the energy of the light wave. So they put a coating in the back, so most of the energy is reflected and you see a good image of yourself. But if there's a glass and part of the energy reflects, you see a good image of yourself, but maybe not so good, the part of the energy is also transmitted. So you usually have both of these things happening, reflection and refraction. Refraction is when the energy transmits into the other medium. Okay, so now let's talk about the refraction and what happens with refraction. Refraction is when the light energy refracts or transmits. The other way to say refraction is transmitting of that wave energy, of the light wave energy, into the other medium. Okay, so let's say glass here. Let's say it's transparent. It will come like this. Of course, some of it will reflect some of the energy, but a lot of it will refract. That means it will go into the medium. So let's say this is the normal line to the surface. This is the angle of incidence. And so if this glass has a higher index of refraction than the air, which it does, so we define something known as index of refraction. Index of refraction. And this is by definition the speed of light in vacuum divided by the speed of light in the medium. Okay, so speed of light in vacuum is the fastest speed that we know of. It's 3 times 10 to the 8 meters per second. And then the speed of light in the medium is going to be usually less than that. So when light enters from vacuum to some other medium, it will slow down. Now the index of refraction of air is about 1.00001. So the light doesn't really slow down too much in air, but actually it ends up that the index of refraction of air depends on the height of the air too. So I'll do a problem like that later on where the index of refraction of the air is changing, and I'll ask how much time does it take a light beam to traverse the distance of the atmosphere if the index of refraction of air changes as a function of the height. Okay, so let's just say for now the index of refraction of air is 1.0001, and let's just say it's constant for now. The index of refraction of water is going to be about 1.33. The index of refraction of glass, of course it depends on what kind of glass. We usually use the crown glass in our examples, and the crown glass's index of refraction is 1.52. Okay, and then other mediums have other index of refraction. Diamond which is this is a part of the reason why dark diamonds sparkle very well. They have very high index of refraction, which means light rays bend a lot when they go in diamond, and they slow down a lot. So I believe the index of refraction of diamond is something like in the range of 2.5 or something. Okay? So now, what's happening? The higher the index of refraction, look at what the velocity of the light is. V equals 3 times 10 to the 8 divided by n. So the bigger the index of refraction of the medium, the n, the bigger, the more light waves slow down in that medium. And if they slow down more, they're going to bend more. Okay? So let's talk about why do they bend. Think about the wave nature of light. If you think about light as a wave, it has wave fronts. Imagine wave fronts like this. Okay? So that when a wavefront comes like this part of the wavefront enters the glass before this part of the wavefront, right? You can think of this almost like ocean waves too. If an ocean wave is coming to you at an angle, and this is the shore, right? You're sitting on the shore, and they come to you like this. As they start getting closer to the shore, maybe the sand is like right here. As they start getting closer to the shore, the shallow part of the water is going to slow them down. So that means this is going to slow down, this is going to be going faster. So this also happens to ocean waves. When they're coming at an angle to the shore, they start bending inward to the normal. Okay? So what happens, in a given amount of time, this part of the wavefront travels a certain distance, while this part travels longer. Okay? So if this one was, let's say, equal time intervals, you can just put your finger like this. Okay? You could just put your finger like this, put it here. But this part is going to be shorter than the other ones, right? Keep all these equidistant. But then this one also keep it equidistant. But here you're going to make it shorter, right? So then connect this and this. What's going to happen? That means this light ray has already gone this way. So it's projecting that the beam of light will bend inward like this. Okay? So if you go a little bit longer time, same amount of time, this will travel the same distance. This will travel the same distance. You see how they've both gotten shorter? Now draw a line. Okay, then draw the same distance. Draw the same distance. Draw a line. And then draw the same distance. Draw the same distance. Draw a line. Okay? So you see what happened? The wavefront bent towards the normal. That means it bent inward. So if you go from air to glass, you're going to be bending inward. You see? So this is the theta refracted. Theta refracted. So it's going to be smaller than theta incident. So what we say is the theta index of refraction of the incident medium times sine of the theta incident is equal to the index of refraction of the refracted medium times sine of theta refracted, right? So if the refracted medium has a larger index of refraction, right? If the n is larger, that means the angle must be smaller, right? So that the sine of the angle, when the angle gets smaller, the sine of the angle also gets smaller, right? So then, when this gets bigger, this has to get smaller in order for it to equal this. This is called Snell's law. Okay? Snell's law. And it's the primary law that tells us the bending of light, okay? When it goes from air to glass. Now, how about if we were to go from water to glass? What would happen? Would it bend inward? Well, water's index of refraction was 1.33, right? And then glass's index of refraction, 1.52. As long as this is bigger than that, right? If this is bigger than that, it still bends inward, but it doesn't bend that much from water to glass because 1.33 and 1.52, not too much difference, okay? Now, how about if it was glass, it would be no bending at all, right? So I've done a demo where I have a glass and I have oil in there, and their index of refractions are similar. It's almost like 1.52 and 1.52, like almost having no difference. And you can see that the clear glass disappears. When I put oil in there and when I submerge it in oil, you can't even see the clear glass. Okay? So how about if we go the other way? How about if NR is smaller than NI? Okay? If NR is smaller than NI, then the angle has to be bigger. The refracted angle has to be bigger than the incident angle. Well, that happens when you reverse the direction of the light beam, right? When you go from a heavier medium to a lighter medium. And by heavier medium, we mean heavier medium as in the index of refraction is larger, right? That medium is heavier, meaning the light rays travel slower in that medium, okay? Now let me just mention one thing before we go on. Even though the light rays travel slower, this equation C is equal to lambda F, right? The speed of light must equal to the wavelength of light times the frequency of light. We're saying that when a light beam enters a medium, its velocity slows down. So the velocity becomes C over N. Now what happens to its wavelength and its frequency? Okay? This is also something we learned when we did this chapter 16, traveling waves. Watch my videos on that if you haven't seen them. I mentioned that when a string wave, traveling string wave, goes from one medium and transmits into another, what happens to the velocity of the wave? Well, it depends on the square root of the tension in the string divided by the mass density of that string. If the velocity goes up, the wavelength goes up, but I said frequency doesn't change. The frequency of the wave is fundamental to the wave. And if the velocity goes down, the wavelength goes down, but the frequency also doesn't change. The same thing is going to hold true for a light beam. A light beam that is red has a certain frequency and a certain wavelength in a vacuum. That red light beam will continue to be red when it goes into glass. Its frequency will not change, but its wavelength will decrease because its velocity decreases, you see. So velocity is C over N, which equals lambda over N times F. You see? So what part of this equation changes? The speed of light divided by N becomes the new velocity of the sound wave. The wavelength goes down by N, but the frequency stays unchanged. So let's say, for example, a red beam whose wavelength is 600 nanometers. Okay? Let's say a red beam whose wavelength is 650 nanometers, color red, okay, goes from vacuum to glass. What will its new wavelength be? What will its frequency be? And what will its velocity be? Right? So we could do a quick question and quick answer. So the velocity will go down by 1.52 because the index of refraction is now 1.52, right? So it's going to be 3 times 10 to the 8 divided by 1.52. So this is about 2, right? That's the new velocity. What's the new wavelength? The new wavelength is going to be 650 nanometers divided by 1.52. So the wavelength also goes down. 650 divided by 1.52, 427.6. 427.6 nanometers. So the wavelength of the red light beam is no longer 600 to 700 nanometer range. In glass, it's going to go down, but it's still going to look red. Now, what's the frequency? The frequency of the red light beam remains unchanged. So what we could do is calculate the frequency of the light beam in vacuum, and then we can say that has stayed constant. So divide the speed of light by the wavelength of the wave, right? Frequency is speed of light divided by wavelength, and that frequency will stay unchanged. Okay, so frequency equals C over lambda, that's 3 times 10 to the 8 meters per second over 650, right? Nanometer is 10 to the minus 9, right? So then we're going to divide here, okay? 4.62 times 10 to the 14 hertz is the frequency of that red light, and therefore that will remain unchanged. And in quantum mechanics, right, we're going to learn that the energy of a wave, let's say the energy of 1 photon of red light, The energy of a wave is Planck's constant times its frequency, right? So if there's one photon of red light, what will the energy of that photon of red light be? Planck's constant times the frequency. Since the frequency of red light didn't change from going from vacuum to glass, its energy didn't change also. So saying frequency remains unchanged is also said to say the energy of the wave remains unchanged, right? It still packs the same amount of energy. So then we multiply Planck's constant, 6.626 times 10 to the minus 34, times 4.62 times 10 to the 14, and that's going to be the frequency, that's going to be the energy of one photon of red light of 650 nanometers, no matter what medium it is in. So we multiply this by, also convert that to electron volts. We can say, okay, one electron volt is 1.6 times 10 to the minus 19 joules. Right? 1 electron volt is the energy that an electron gains or loses when it goes through a potential difference of 1 volt. So if we divide this by 1.6, you see, so if the red photon has a wavelength of 650 nanometers in vacuum, it has always that same frequency, no matter what medium it is in. It always has an energy of 1.91 electron volts. Okay, so that's what it means to say the frequency and energy remains unchanged. Okay, now if I reverse the process of the refraction, okay, what's going to happen when I go from glass to air? Or from water to air, let's say. Water to air. Okay, so the light beam is going to speed up. So if we call this the incident light beam coming from water, it's going to refract in such a way as that speeds up, right? So now the refracted angle is going to be larger than the incident angle. So we say it refracts outward when it goes from a lighter medium to a heavier medium. So it's basically the reverse of the backward, of the other way. So if the light beam is coming this way, and then it goes in this way, this we call incident angle, this we call refracted angle. But then we can reverse that light beam and still draw the two same light beams. Now we call this incident, we call that refracted, right? So now you can see that it refracts outward. So if I put a pencil or something in a jar of water, so imagine you have here water, and I put a pencil or some rod, what's going to happen, right? So what happens, let's say the tip of the pencil, the beams of light comes out, straight beam of light comes out, goes this way, then this beam comes out, refracts, right? Then this beam comes this way, refracts more, right? So what does it look like? When you're looking at it from here, and you trace these beams of light backward, it looks like the tip of the pencil is here. And the same thing will happen to all portions of the pencil. They will appear to be higher up than they actually are, right? So this part of the pencil will appear to be here. This part of the pencil will appear to be here. This part of the pencil will appear to be here. So the pencil will look bent like this. Okay, so this is the original pencil right here. Let's make it a sharp pencil. This is the original pencil. So because of the refraction of light, objects in water or glass will tend to be closer to the surface than they actually are. That's why your windows, in the side windows, it's always written, objects in the window are always appear to be closer than they actually are. Well, same thing with objects in water, fish in water, pencil in water. They will always appear to be closer to the surface than they actually are, and that means they will look bent when you place them in water, right? There's an interesting other phenomenon that is related to this, and it's called total internal reflection. So what happens when I increase the angle more and more and more? Right? When I increase the angle more, imagine this is water. Right? So this is, let's say, a beam of light. Right? Beam of light is coming out like this, going like this way. So if I angle the beam of light kind of more steeper, it could go like this, right? And then what will happen? Instead of coming out, it will basically kind of stay trapped in. It's going to go like this and glide along the surface, right? So if the beam of light was coming like this, it's going to escape. Beam of light like this, it's going to go like this. This beam of light is going to go like that. So there's a certain angle that's called the critical angle, theta critical, where if I aim the beam of light that direction, then the beam of light glides along the surface and it stays trapped. Any angle larger than that critical angle, right? If I aim the beam of light this way, any angle larger than that, majority of the energy of the light gets reflected back. Whereas these beams of light, some of the energy gets transmitted, other portions of the energy gets reflected, but not too much get reflected. Majority of it escapes. The transmission becomes a lot more than the reflection. So then I aim it a little bit this way, transmission is more than reflection, see? All of these beams are getting refracted and reflected. But now, if I aim it at the theta critical, majority of the energy refracts this way, majority of the energy comes back. And then if I go either any angle larger than that, then most of the energy is trapped in, right? So this is called total internal reflection. Why total internal reflection? Any angle greater than theta critical, an angle greater or the same as theta critical, causes most of the energy of the wave to reflect back into the medium. Okay? Causes all or most of energy to reflect back into medium. I also have video on that where I show you the concept of fiber optic technology and how it works, that a laser beam is shot at a steep angle through a glass medium or through fiber optics, and we contain that energy of the laser beam inside of the fiber optic, and we can transmit energy for miles and miles and miles like that without much attenuation of energy, without much loss of energy. So we use this concept all the time in a technology known as fiber optic technology. We also use this even for swimming pools. When we design a pool of water, when we design water in there, when we put a beam of light, we usually put the beam of light kind of high up like that, right? If we put a light source, we kind of put it high. Why do we put it high? Well, because most of the beams of light emanating from the beam of light are going to be what? The angle, this angle is going to be larger than the critical angle, right? Like that. So if we put the beam of light at a certain corner at a very high elevation, close to the surface of the water, most of the light energy is going to get reflected back. Okay? When it gets reflected back, it will help us see the bottom of the pool. It will reflect back and it will stay inside of the pool. It will illuminate all surfaces of the pool, including the bottom of the pool, and it will help you to see the pool. Now, if you had placed the beam of light on the bottom, what would happen? Like this. So then this beam of light would go, most of the energy would go like this. So it wouldn't reflect back, you wouldn't see this portion of the pool very well. All you would see is the source of light, the light would emanate, and then you would see you would actually see the source of light itself, not the reflection from the surface. So then this beam of light would go, most of the energy would refract. This beam of light would go, most of the energy would refract. So all these people that are standing here, okay, they would actually just see the light source. All this surface of the water would be unilluminated, right? So that would be weird if you actually just see the light source itself and not the surface of the water. Maybe people standing here, okay, maybe it reflects back like this at a certain angle. Maybe if you're way at the corner here, you'll see this portion of the pool lit up. The way on the far corner. That surface of the water will be lit up, but most of these area of the water will not be lit up. You'll just see right through it, and you'll just see the light, the actual source of light itself. So you won't see the bottom surface of the water and the top of the water. So In order to prevent that, we put the beam of light up there so that most of the energy reflects, and then you see a nice reflection from the bottom and the top, and you see the surface of the water and the bottom of the water, right? So in the design of the location of the light, that also affects it, and also for fiber optic technology, that's also very important, okay? So how do we calculate the critical angle, okay? The critical angle, how do we do that? Well, we're just going to put this requirement. Theta incident is going to equal to the critical angle, and then we're going to assume the critical angle is the angle where the refracted beam of light glides along the surface, so the refracted angle is equal to 90 degrees, right? So this is going to be n incident sine of theta critical, right, this one, and that's going to equal, this one is going to be n refracted sine of 90, right? N incident sine of theta critical, and then this is the n of the refracted medium sine of 90. So the equation for the critical angle therefore comes out what? Sine of theta critical is equal to nr over n incident. Of course, this only will occur if the index of refraction of the refracted medium is less than the index of refraction of the incident medium. So nr has to be less than ni. Okay? So this is also an important concept, total internal reflection. Okay? One other concept to talk about in this theory section, and that is the fact that the index of refraction of a medium is also wavelength dependent. The index of refraction of a medium depends on wavelength. Okay, this is why when a white beam of light comes into a prism, it spreads into the different colors, because all the different wavelengths of light spread out unevenly. Okay, so it ends up, let's say when we say the index of refraction of glass is 1.52, that is kind of an average value. It depends on the frequency and wavelength of the light entering the glass. The index of refraction of red is the least. Red, let's say it's 1.521, right? Index of refraction of blue and violet is the most. And glass of, let's say, violet is going to be 1.523, something like that. They're going to be close to each other, but slightly off. Maybe we can say 1.524. Okay? So the different colors of the rainbow, Roy G. Biv, red, orange, yellow. So orange is going to be slightly more than 1.521. Yellow is going to be slightly more than orange. Green is going to be somewhere in the middle. Let's say green is 1.52, let's say 523 or 522, right? Then blue is going to be closer to violet, and then blue, indigo, violet. So the violet is the most. So we say red refracts the least out of them. Why? Because the index of refraction of the red is the smallest. That means red doesn't slow down as much, right? Red doesn't slow down as much. So when a white beam of light is coming, let's say this is the glass, let's say this is white, okay? When red enters glass, it doesn't slow down as much as the other wavelengths of light, right? So it's the red will be like this. So let's say this is the original direction, right? So red will be like this. Right? So it's bending, but not as much as the other ones, right? And then violet and blue will be the most. So violet might look like this. Indigo and then violet, right? So the red refracts the least, violet refracts the most. And so what happens? White light goes through the glass and it separates out into the different wavelengths of light because they refract differently, and you get the dispersion. It disperses out. That's why you also create a rainbow. When you have water droplets in the sky, they act like glass, they act like water in the air. The sunlight goes through them. The red light refracts the most. No, so the red light refracts the least, and then the blue refracts the most, and then the white light, the light of the sun disperses out, then you create an arc with a rainbow, right? The different colors of the rainbow. So the first person, one of the first persons to investigate this very thoroughly was Isaac Newton himself, the same person who discovered the law of gravity. He did a lot of experiments with dispersion of light through prisms, okay? So with this now, we'll do some examples next, and you'll see how all of these equations are utilized. Thank you.